Welcome to this video about split-step wavelet. Split-step wavelet consists in propagating an electromagnetic wave on long distances, taking into account the ground and the atmosphere. Just as the well-known split-step Fourier, this propagation is splitted in steps in free space and steps to account for the environment. This video focuses on the free space step, which differs from SSF. To do so, let's take a 2D example of propagation. On the left, you have the field right after the phase screen at x, and on the right, you have the field right before the phase screen as x plus delta x. Let's look how we go from one field to the other in free space. To make a propagation on a step delta x, we first make a wavelet decomposition on the first field. Then we propagate this wavelet decomposition directly in the wavelet domain. After that, we perform an inverse wavelet transform to obtain the field on the right. Question is, how do we perform this wavelet propagation in free space? So what we have here on the left is the wavelet decomposition of the field at x. What we want to obtain is the wavelet decomposition at x plus delta x. To calculate this, let's suppose we know the propagated wavelet for each wavelet coefficient. If we know this, then we just have to sum all the contributions for all wavelets in the wavelet domain. Next question is, how do we know the propagated field for each wavelet? Let's take this wavelet here on phi 2. With an inverse wavelet transform, we can obtain the field corresponding to this wavelet here. Then we propagate this field on a step delta x in free space, whatever the technique used here. We make a wavelet transform to obtain the corresponding wavelet decomposition. Finally, we apply a hard compression to have a sparse wavelet representation of the propagated field. This calculation will be repeated for each wavelet. The scaling function first, the first wavelet, the second wavelet, the same with one translation, and the third wavelet, same with 3 translations. At the end, 2 power L operations are necessary. Here, L equals 3. We have obtained our dictionary of propagators. With these 8 propagators only, and using the translation invariance of the wavelet decomposition, any signal in the wavelet domain can be propagated in free space. This operation can be made before the propagation if my propagation step is constant, or can be made on the fly if I want to change my geometry during the propagation. So finally, to summarize, to propagate my wavelet decomposition in free space, I use my library of propagators. Then for each coefficient, I know the corresponding coefficient, and finally, I make a compression on the field itself to keep only few coefficients. An inverse wavelet transform gives the propagated field, and the environment is finally accounted in the space domain. That's how we obtain iteratively our total electric field. Thank you for listening.